Hi, we're Team 19, and this is the analysis and redesign of a kick scooter. Some background about kick scooters: they were a children's toy used for transportation and play, but they can also be used as a piece of extreme sports equipment on ramps and in parks. The scooter itself has one fixed wheel, and the front wheel is turnable for stability and control, and they're usually made from an aluminum body to be lightweight but robust enough to withstand wear and tear. Looking at our production and target customers, we estimate the production volume is going to be around 300,000 units per year. This is going to be for our primary customers of distributors and our secondary customers of end users, including recreational scooter riders and sport/trick scooter riders. Here is the CAD and part list for our scooter, including an exploded view of our wheel subassembly. Going to our product analysis, our fast diagram here includes our main functional branch of rolling on the ground, with our assured dependability underneath that, including maintaining speed, providing stability, and controlling the direction of travel. For our functional component mapping matrix here, you can see that many of our different components fit into the same different functions, so we're going to be able to look at that later as potentials for redesign. With this, our quad chart here shows that we have high functional importance and high manufacturing/assembly costs on our deck, handlebar, fork, and clamp, which are things that we are also going to be looking at for potential redesigns for assembly or manufacturing. For our product family design, we are looking at the functional differentiations between our different customer groups. And here, I want to note that our customer groups are differentiating between our end users, so this is between the trick riders and the more casual riders. Looking here, our platforms are going to be shown on the left there, with our modules being the bearings used in the wheels, the deck, and the grind pegs. This is our original CAD of the original, more casual scooter, and this is the CAD for the scooter for tricks. We added grip tape to add grip and control, and we added bars to allow the rider to do grinds and have a little extra style. Looking at our product family assembly diagram, we could originally assemble this scooter side by side with the regular style and then the scooter made for tricks, but to improve upon this, we differentiated at the decks, creating this forking PFAT design.
When choosing parts to redesign for our design for manual assembly phase, we wanted to target parts that had shared functions with other parts in the assembly. Here in our function component mapping matrix, we can see that both the deck and wheel have functions that overlap with other parts, making them prime candidates for redesign. This part selection is further verified by our quad chart. The deck of the scooter has both a high cost as well as a high functional importance, which is a good indicator of a part to be reworked in our assembly. For the wheel, while it can be considered to have a low cost, it still has major functional importance, and we saw ample opportunities for a successful redesign for this part.
To calculate the current assembly efficiency, we calculated the theoretical minimum number of parts necessary in the scooter, which is 12, and multiplied that by the average time for a part with no difficulty in handling and insertion, which is about 3 seconds. Then divided their product by the total manual assembly time, which was calculated based on values we found earlier in the bill of materials. This provided us with an efficiency of 0.12.
For the deck of the scooter, we identified 3 main design for manual assembly changes to help improve the product. Firstly, we added grooves to the cylindrical part of the deck to help with making fitting the handlebar mechanism go more smoothly. Additionally, we made the back end of the deck, where the back wheel is attached, more accessible by shaving off some unneeded material. This allows for easier hand and tool access during assembly. Finally, we decided to make the part more symmetrical by shifting the cuts in the deck to be perpendicular with the edges of the deck. These changes had no major impacts on the functions of the deck and provided a slight decrease in the manufacturing cost due to the removed material.
For manual assembly design changes in the wheel, we decided to remove the need for a spacer by extending the inner ring of the wheel to reduce part count. We also added a chamfer to the outer rings where both the bearing and axle are pressed through to increase ease of insertion during assembly. Lastly, we added a small lip around the outer edge of the wheel to allow the tire to slide on and stop at the exact distance necessary. This provides a locating feature and removes all necessary precision. Overall, these changes allow for easier alignment of parts during assembly, which will reduce the assembly time and save money. Removal of the need for spacers also reduces this assembly time and saves money on additional parts needed to be ordered.
For design for automated assembly, we decided to look at the fork, handlebar, clamp, clap screws subassembly because it only covers 3 different functions and we saw a means for improvement. This is also shown in our quad chart, showing that these both have high manufacturing assembly costs as well as high functional importance. This is the original fork handlebar assembly. It has 2 clamp screws going into the clamp, which combines the top handlebar sliding over the fork. For improvements, we decided to reduce the fasteners in the clamp, increase the parsymmetry in the fork by reducing the offset, facilitating orientation with the clamp by creating that offset where the screw goes in, creating easy insertion for the handle, adding a chamfer on the inside to make it easier to slide over the fork, then preferring Z-assembly by making the clamp screw go in vertically instead of through the side. Functionality: steering would be slightly changed, but not critically. And then for cost, we understand the fork will be easier to machine now because the offset is gone, but the clamp would be more expensive to make, but these should offset each other.
We chose our manufacturing process based on a variety of factors with both of our parts. The wheel is made from aluminum. It is a 3D solid with critical dimensions of 24 by 74 by 74 millimeters. Based on this, we can eliminate processes such as injection molding and thermoforming that are exclusive to non-metal materials. We can also eliminate centrifugal casting, extrusion, and sheet forming based on the shape. The wheel weighs 121.99 grams, which eliminates sand casting as a possibility. The minimum section thickness of 1.5 millimeters is found at the spoke of the wheel and eliminates investment casting and forging as potential processes. We chose the tolerance of the wheel to be plus minus 0.1 millimeters because any imperfections with the profile of the wheel or the location of the bearing relative to the center will be very noticeable while riding. This tolerance requirement narrowed our options down to electromachining and conventional machining. Our surface roughness was less than 1 micron, which both of our remaining processes can achieve. We eventually chose conventional machining because it is much more suitable for mass manufacturing economically and can reasonably meet our demand of 600,000 wheels. For the deck, we are also working with an aluminum 3D solid with critical dimensions of 110 by 155 by 590 millimeters. Like the wheel, this eliminated many potential processes. The mass of the deck is 1,062.77 grams, which is feasible to produce with sand, dye, investment casting, forging, powder methods, and both electro and conventional machining, as well as additive manufacturing. The minimum section thickness of 1 millimeters is found at the rear fender and narrows down our options to die casting, electromachining, and conventional machining, as well as additive manufacturing. We specified the tolerance of the deck to be plus minus 0.5 millimeters because the deck does not need to be quite as precise as the wheels, but should still have a high quality standard. Our surface roughness was again less than 1 micron, which still leaves us with die casting, powder methods, electromachining, conventional machining as potential choices. However, when it comes to economics, die casting was a clear winner because of our large batch size of 300,000 decks. Conventional machining is also a potential process, but would be very labor and material intensive compared to a straightforward die cast.
For the DfM analysis of Part 1, the scooter deck, we used the provided die casting formula. We found a total per part cost of $9.44, assuming a single cavity mold. For changes, we reduced surface complexity in the rear and avoided sharp internal corners. We simplified the neck area to reduce weight and the number of side pulls, and we removed internal overhang features from the bottom of the deck. After our redesign, due to decreased part volume, number of side pulls, and overall better surface complexity, we had a new per part cost of $4.77. The reduced weight may have a slight impact on stability, but will improve transportability. No symmetry or interface surfaces were affected by the redesign. The only things that would affect assembly are the increased tool clearance in the rear, as well as the lower weight making handling easier.
The second part we performed a DfM analysis on was the wheel. Using the formula on the top left, the calculated cost per part was $3.81. To verify, we created estimated quotes for various quantities using hubs.com. We extrapolated the data to create the fitted curve seen on the bottom right. We found that for the quantity of wheels we plan to produce, the curve predicts the price to be $4.56. If we assume that the manufacturing is 80% of the quoted price, then the estimated manufacturing cost is $3.65. The suggestions generated by DfM Pro are that chamfers should be used over radii for outside corners. The second one is creating designs which use standard hole sizes, and the bottom suggestion is about how the feature is not accessible by any tooling because of the undercut. The three design changes we decided to make based off of the design for machining guidelines are to replace the old complicated cuts in the wheel with circular ones, which fulfills DFMC-3. Next, we replaced the curved surface of the wheel to the flat one, which fulfills DFMC-6. And finally, we added a radius to the internal corners of the wheel, which fulfills DFMC-11. We performed a DfM analysis on the redesigned wheel and calculated the cost per part was $2.59. Again, we created an estimated quotes for various quantities using hubs.com, then extrapolated the data to create the fitted curve seen in the bottom right. We found that for the quantity of wheels we want to produce, the curve predicts the price will be $3.46. If we assume that the manufacturing cost is 80% of the quoted price, then the estimated manufacturing cost is $2.77. The functions we stated earlier that this part has are that it rolls on the ground, maintains speed, and controls the direction of travel. The redesign does not improve or worsen the performance of any of these functions. The impact on the assembly is also minimal because the redesigned wheel used the same features for alignment, and therefore the assembly time does not change. When considering the overall cost for producing the scooter, because the part is used twice, the total cost is reduced by $2.44 when using the redesigned wheels.
There are a lot of potential services we could offer, including a monthly maintenance plan, ride sharing, or even a subscription for parts that deteriorate quickly like bearings. For environmental impact, scooters might reduce car usage across short-distance commutes, and the fact that our construction is strong and reliable means less waste over time. Providing people with a low-cost source of fun and transportation is very beneficial. Overall, our redesign succeeded in decreasing cost and improving assemblability.
Next time, we would like to explore the potential for many environmentally friendly manufacturing and material sourcing techniques. We would also like to try and minimize rubber and plastic parts.